Hi, my name is Eric Wing. I will be talking about the library IUP, or YUP, today. I learned last year at the Lua workshop that it's pronounced YUP. Old habits die hard, so sorry in advance for mispronouncing it. Very quickly, I'll give you my background. I worked on a global satellite communication system called Globalstar. It involved launching satellites into space with rockets. It's not relevant for this talk, but everyone says it sounds cool. I've done a lot of cross-platform development. I started in scientific visualization. It eventually led me to becoming a macOS 10 Cocoa expert to build deeply integrated native UIs with OpenGL visualization systems. I wrote the world's first full-featured bridge between the Lua language and Cocoa. I gave a talk on this last year at the 2016 Lua workshop. I co-authored the book Beginning iPhone Games Development, published by Apress. I worked on some commercial game engines. I was the chief architect for the current SDK, which allowed people to write native cross-platform games in Lua. I later co-founded Atlantica to build a game engine for Appcelerator, so people could write native cross-platform games in JavaScript, embedding JS like Lua. I also gave a talk on this last year at the 2016 Lua workshop. Since Android is so painful, I was forced to become an Android expert to help out. I am currently working on a cross-platform SDK to make native app and game development simpler, called Blur SDK. With that out of the way, let me quickly introduce IUP to everybody for those who are not familiar with it. IUP is a library designed to help you build native user interfaces in a cross-platform way. It was developed at PUC-RIO, the same university as Lua. In fact, it started as a research project in the mid-90s, and you may recognize that one of the Lua authors is on this paper. It is MIT licensed. Look at the list of backends. You'll notice that macOS 10 is missing from this list. I believe this is why IUP remained relatively obscure and unknown, even though it has been around for so long. That is a hard platform to ignore when talking about using a cross-platform GUI library. So that's where this talk starts. So let me tell you my personal story of what led me to IUP. I have been creating a new SDK called Blur, originally designed to make cross-platform mobile and desktop native game development easier. My co-presenter Chris describes it as Create React App for native development. The core set of libraries consists of many PRC libraries for maximum portability and performance, but also to allow language bindings. So Blur officially supports writing in C, Lua, JavaScript, and Swift. I showed a couple of shots last year in my JavaScript talk. But to make things really great, I realized I needed GUI tools. For example, one feature of Blur is that it provides a centralized cross-platform build system built on CMake, which allows you to simply list your project files in one text file, but you get out native IDE projects such as Xcode, Visual Studio, and Android Studio, so you can use the native tooling for each platform and without needing to manually keep them all in sync. While I could reuse the same game technology to make some of them, like this particle designer, there are a lot of things that really should be more native. Since this feature launches other programs, it should be lightweight and not take much CPU or RAM. And it should not require a lot of screen real estate since the typical workflow will have multiple applications open at the same time. So a large OpenGL window encompassing all widgets isn't ideal. Since I support developing on multiple platforms, I didn't really want to write different GUIs for each platform. I've been in cross-platform for a long time, so I've used a lot of different toolkits, WXWidgets, Qt, Java, TK, NodeWebKit, and so forth. I just like all of them. For time, I'm not going to go into details about all of these, but this time around I decided to go with Qt Quick. While I've done some old Qt before, Qt Quick is a relatively new feature/rewrite that the Qt community has been pushing developers to use. So I decided to finally give it a try. In the end, I was very unhappy. I'm going to skip describing all the bugs and details, but I did get something that eventually worked. But as somebody who spends a lot of time on Mac, I hated the user experience of my own program. My program is, in the grand scheme of things, very simple, not much more complicated than a Hello World or calculator. But why does my app eat up so much more RAM? Depending on the platform and how you measure it, it can be like 4x. Similar result on Linux. Why does my app take so long to launch? Watch how many times the icon bounces in the dock. Compare this with native. And the GUI experience wasn't truly native. For those who don't know, Qt isn't fully native. They re-implement their own widgets, but happen to have really good skin artwork. But Mac users like me quickly feel where everything is wrong because there is a lot of subtle behavior that Qt does not reproduce. And I don't want to pick on Qt too much here because most of the other toolkits are far worse. But I had a working program. I wasn't happy, but it was good enough. Then, one day, I needed to add Raspberry Pi support. And at the time, Qt Quick on Pi could not support this due to the way it uses OpenGL for rendering its non-native widgets. And even if it could, the RAM is really tight on the Pi, and I was already complaining it took too much RAM. Furthermore, the default windowing kit on Raspbian is GDK-based, not Qt-based, so that would make it even worse. So Raspberry Pi was the straw that broke the camel's back for me. But what was I going to do? I still didn't want to write different apps for each platform. But I really needed something truly native. It would not only solve my Raspberry Pi problem, but also the user experience problem that was causing me to hate using my own app. Oh yeah, there's IUP. IUP is cross-platform and truly native. The reason I skipped it is because it didn't have Mac support. But I'm an experienced Cocoa developer. I know how to fix this. I started counting how much time I've wasted over the years trying to work around the lack of a good native cross-platform library. The world really needs this, but nobody wants to build it because it's hard. But I have the skills to do this. It's time to fix this. So, as I already gave away in my previous clips, I already rewrote my tool in IUP and started writing the Mac Cocoa backend. Because I really hammer the native UI thing, I need to demonstrate why native UI matters. I already mentioned RAM and performance, but usability conventions are important too. Each platform has their set of conventions and features that users come to expect, and if your app doesn't behave like every other app on the platform, people notice and become unhappy like me. If I wanted my Mac to behave like Linux or Windows, I wouldn't use a Mac, and vice versa. So, let me quickly show you some interesting Mac features that non-native cross-platform GUI libraries frequently miss. All Cocoa text views have the ability to select discontinuous blocks of text, even vertically. First, I select all the vertical numbers and cut and paste them. Then, I select discontinuous words and cut and paste them. This feature I use heavily on Mac for all text views, so when apps screw this up, it irritates me to no end. Command-E will put the currently highlighted text into the find buffer. Then Command-G will find the next occurrence of the word in the current focused view. In this example, native Cocoa is at the top, Java-based Android Studio is at the bottom. I want to find all occurrences of the word malloc in this file. So, I highlight the first malloc I see and hit Command-E. I then hit Command-G multiple times until I wrap around the document. But when I use the non-native app, Command-E does the completely wrong thing and pulls up a recent files dialog, and Command-G does absolutely nothing. Macs have a ton of features packed into the menus, and Apple's built-in behaviors and UI guidelines result in apps supporting the same features in every app. They also have something called services that can talk to other apps. Here, I want to capitalize my words. Notice the native app on the left has a conventionally packed menu, while the app on the right is missing most things. You can bring up a dictionary service for any native Cocoa text. Notice again how it fails to work on the right. Because of some of my past work in audio, I have been contacted by people with impaired vision. I always feel a tremendous amount of guilt because those projects I worked on never spent resources on this. The video game industry is the absolute worst at being accessible. But If I at least use native UI, those users have a fighting chance because the big platform vendors spend a lot of resources to make their platforms accessible and apply automatic behaviors to any apps that use their native widgets. So here are two very simple examples. There are built-in options for people with impaired vision which can change how widgets look. In this screen, the native apps are on the top left and top center. Qt is at the top right. The Java-based Android Studio is bottom left, and the Electron-based Slack is bottom right. Notice as I toggle the high contrast option, the native rendering changes, but nothing happens with the non-natives. It is worth noting that on iOS, when they move to flat design, the buttons start looking like labels. If you turn on accessibility features, those buttons will actually be drawn differently, so you can clearly see they are buttons. Here, I want to use the speech recognition for the text entry. Native is on the left, Qt is on the right. Hello, world. IUP researched how to solve the problem of creating native user interfaces in a cross-platform way. The problems are as follows. How can you make a cross-platform interface when the native interfaces for every platform are so drastically different? Additionally, since every platform uses a different programming language for their native development, how do you deal with this in a flexible and cross-platform way? For example, Qt is implemented in C++ and expects you to subclass to override things. But remember, Qt isn't native. If a native widget is implemented in C on GDK, Objective-C on Mac, Java on Android, and so forth, it is not possible to subclass a C++ class in any meaningful cross-platform way to alter the underlying widgets implemented in a different language. IUP solves these problems in the following ways. IUP's core and public API are implemented in pure C, because C is the one language that every language can talk to. Platform backends are implemented in each platform's native language using the native widget set. IUP does not employ language subclassing since it can't be expected to work across all platforms. Instead, IUP uses attributes to set properties. The advantages are they can scale to cover entire native API features. It does not require breaking or changing the API. Unsupported properties on platforms can simply ignore the feature request, and it makes IUP simple to use. IUP also recognized that not everybody wants to write in C, so the API was designed with language bindings in mind. Since this is PUC-RIO, Lua bindings get first-class support. To address the different sizing and layout problem, IUP invented a textual layout description format called LED. It is optional, but it can be very convenient if you want to make slightly different layouts for different platforms while keeping your code unchanged. IUP also has a live in-app runtime layout editor. The real app GUI is on the left. The layout editor is opened on the right. Watch as I move some buttons around. We won't be focusing on these in this talk, but just so you're aware, IUP has accessory libraries. IUP CD for Canvas Draw provides access to native 2D drawing APIs in a cross-platform way. Then on top of IUP CD, there are a bunch of other libraries that create custom, cross-platform, non-native widgets, sort of like Qt. There is also IUP Plot, a plot graphing library built on IUP CD, and there's also an IUP GL library. Finally, let's talk about the Cocoa backend for IUP. Just so everybody's on the same page, Cocoa is the name of the framework you write native Mac applications in. It provides widgets like text, buttons, and windows. Objective-C is the native programming language you write Cocoa applications in. It is a 100% pure superset of C. Objective-C adds an object system and powerful runtime inspired by Smalltalk. So the Cocoa backend for IUP is implemented in Objective-C. For the most part, the Mac Cocoa implementation is pretty straightforward and matches well with Windows and GDK. IUP Cocoa isn't finished yet, but sometimes when I say that, people assume the worst and nothing is implemented. It is actually further along than most people think. I just started shipping my Mac IUP version of Blur GenProj. So, here are some screenshots of things that have been implemented to various degrees. The top left is Windows, top right is GDK, bottom is Mac. In this, we have a basic dialog with labels and buttons. Somebody specifically asked me if Unicode and complex text layout worked. For example, does the word peace in Arabic get displayed correctly and in the correct right to left order? The answer appears to be yes. Text, progress bars, tree, calendar, file dialogues, canvas. Of course, not everything is rosy and perfect. I want to highlight two of the more interesting differences. Currently in IUP, you are expected to have complete control over the event loop. There is a function called IUP main loop, which basically is a while loop that keeps pumping the event loop until the app quits. On Mac, you can't really do this. Apple expects you to call a method which starts Apple's event loop, and Apple wants complete control of the loop. Some game devs in the audience may know APIs to get around this, but there are a whole bunch of things in Apple's frameworks that assume the proper event loop and break when it is not used, so we can't do this. We'll come back to this topic later because you'll see a similar event loop problem appear 3 more times in this talk. Other desktop environments like Windows use per window menus, but Mac doesn't have this. Instead, there's a single global application menu. After a lot of experimentation, I decided the best way to go about this was to ignore the per dialog IUP set attribute and Shanghai the IUP set global API for this purpose. Unfortunately, this means the user needs to add a new case to opt into the Mac application menu. But to help make things easier, I make IUP provide a default menu pre-populated with all the normal stuff. The backend will automatically merge manually added menu items with the ones that are in the default, which avoids duplicate entries and allows overriding default behaviors. I should mention that Cocoa was originally invented in the mid-late 80s at Next, Steve Jobs' company after Apple. A joint effort between Next and Sun Microsystems tried to push it as a cross-platform environment called OpenStep. That didn't get much traction, but there was another implementation called GNU-Step, which still survives today. Somebody already forked my IUP Cocoa branch and modified it to work with GNU-Step on Linux. So that's IUP Cocoa. But it's 2017, not 2004. The world has shifted to mobile. 270 million PCs shipped in 2016 compared with 1.5 billion smartphones, and PC sales are on the decline. Google is switching to mobile-first indexing. Mobile game revenues are now larger than PCs and consoles. So, to be really useful in today's world, we also need to talk about IUP for mobile. The good news is that IUP's thoughtful design seems to be flexible enough to handle mobile already. For example, attributes already avoided APIs from getting deeply entrenched with desktop-only things. So yes, we can do this, but it just requires some careful thought about how things should map and work on mobile. So, let's go through one of these thought exercises. What does dialog mean for mobile? On mobile, we don't really have space for multiple windows. On iOS, there is a class called UI window which shares similarities with the desktop window, where it is a full-screen window that serves as a view container for all the widgets on screen. A naive mapping would suggest that we map this as the dialog, but the problem is multiple dialogs. UI window by itself isn't particularly useful without more complicated user interfaces to manage multiple UI windows. Safari is an example of this. You can see that Apple has designed a special custom user interface to let users select between multiple windows. But most apps don't do this because this is actually not the common case on mobile, and this UI is kind of complicated. The more common navigation element on mobile is not arbitrarily selecting between windows, but joined down and back through a stack of views. We start on a first screen and select an option which pushes a new view. We continue drilling down until we are done, and then pop our way back out from the stack. This is true on both iOS and Android. So my proposal for dialog, at least as the common default, is to map to this kind of navigation structure. On iOS, we use UI Navigation Controller, and Android, we use Activity. Every time we create and show a new dialog, it pushes into the navigation stack. Since we are leveraging native OS widgets and paradigms for this, users are presented the common UI they are used to and know they can navigate back. On iOS, Navigation Controller gives you the back button on the nav bar. On Android, users know to use the back button. So, let's implement it and put everything together to see how a singular IUP program can be made to work naturally for all platforms. This is a simple IUP program written in Swift. You don't need to understand this code, but this program creates a dialog containing a button. When you press the button, it creates a new dialog with a button, and so forth. So here is the program running on Ubuntu Linux. Since I mentioned Raspberry Pi before, here is the same program on a Raspberry Pi. Windows. Now we're on Mac. Now let's do iOS. We are mapping dialog to use UI Navigation Controller and UI View controllers under the hood. And finally, Android. Here we map dialog to activity, which is a little like iOS View Controller. So implementing IUP for iOS is pretty straightforward aside from all the thought exercises. I do want to mention that the event loop design problem is on iOS too. Apple wants full control of the event loop. So let's talk about Android. For developers that haven't done any Android development, there are a lot of assumptions, myths, and misconceptions about what you can do and how things work. So I'm going to dispel them right now. All Android apps must be written using the Android SDK, which is in Java. You cannot escape this. Android's GUI APIs are completely in Java. Android originally was Java only, but had to cave to game developers, and they provided the Android NDK, which allows for C and C++ development. Unfortunately, the Android NDK is awful. Legendary game developer John Carmack of Doom and Quake fame called it, quote, half-baked, and says it, quote, really does suck. People like to remind me that Carmack has rarely complained about developer environments, even ones that were notoriously famous for being hard, such as the Sega Saturn. So this is damning. But this quote went viral because every NDK developer knows this pain. The NDK is a second-class citizen on Android with poor integration. The Android NDK provides very few APIs, and they have no APIs for native GUI. So, to get native GUI from C, you must use Java JNI to cross back and forth between Java and C. I've given multiple talks bashing the NDK. For more details, check out my JavaScript talk from last year. Also check out my Swift on Android talk from earlier this year at the Try Swift conference in Tokyo. I'm not going to repeat those because I have other Android problems I need to bash in the context of IUP. Another horrible thing about Android development is its use of God objects. In Android, a large number of APIs require a context parameter. And of course, Android couldn't be bothered to give you a standard API to get a context. This one choice has made it a nightmare for authoring libraries, especially for pre-existing cross-platform libraries which never needed a platform God object to be explicitly supplied with most API calls. Imagine all the pre-existing libraries that call fopen. You must change every instance of this to call an Android replacement. Okay, fine. Function rename wrappers are easy, but now you must somehow also acquire a context instance and pass it as an additional parameter. But there's no standard way to get a context. Of course, the reality is nobody's going to do this, and everyone tries to find an awful workaround for it. The most common source of a context is an activity class. A common mistake cross-platform libraries make trying to support Android is to hold a reference to a particular activity. But because activities are intended to come and go at will, it is incorrect to hold a reference to one and keep it rooted past its expected closing. So, there's another object called the application, which fortunately does last the life of the entire application. But, as before, there's no standard API to get the application context. The typical pattern is to create your own subclass of application, force it to be the application class, and implement your own getter so you have a way to retrieve it throughout your own application. So this is what I've employed for IUP. On Android, Android controls the event loop, period. You must never block the event loop. You cannot manually pump the event loop. Also note there is no int main because we are in Java, not C. A big but common mistake is to work around the event loop design by putting the NDK in a background thread. It's a mistake because Android GUI APIs must be called on the main UI thread. I've been through this with multiple companies across different products and compared notes with other experienced Android developers, and this always ends in tears when you extend beyond your original base case. Google made it worse because they have an example called native activity which does this. It has steered so many people in the wrong direction. It is a disgrace. I don't have time to go into detail of the problems this causes, but at a high level, you now end up locking everything for safety, which ultimately kills performance. You now can no longer just directly call a system API because you must redirect everything to happen on the correct thread. Users now must understand the threading models of their app, the framework, and the OS. Implementation detail has leaked into everything. And time again, I've seen race condition bugs happen during application lifecycle events like background, resume, and quit, which is hard enough to get right even when single-threaded. So, IUP Android is unapologetically designed to be on the main UI thread. But there's one more major platform to talk about, the web browser. For the past few years, web developers have been trying to make native apps, and unfortunately, they are bringing their bloat and bad ideas about the DOM into our native environments. So, this is my revenge. Turnabout is fair play. Let's build a web backend for IUP so we native developers can go in the other direction and build web apps with all our bloat and bad ideas. Ha! But while I know JavaScript in non-web contexts, I actually don't know much about the DOM and the web browser. Fortunately, I got really lucky and found Chris Matzenbach, who's an expert on these matters. He's been doing the heavy lifting for this backend, so I turned the talk over to him.
Ever since the early 2000s, we've had a battle in the industry between writing native programs or writing applications for the web. Everyone has their preferences, and it's clear this battle won't be won anytime soon. Thus, why not hedge our bets? Why don't we treat the web browser like any other platform? This is the core idea of IUP Emscripten. Let's take our native programs and deploy them to the web browser, as if it were any other platform. One of the problems up to this point has been JavaScript. It's the only language you can use to write applications for the browser. Native developers don't use JavaScript for many reasons, and thus a rewrite has always been required. But now, thanks to the Emscripten compiler, we can change that. This new tool allows us to bring additional languages to the web browser, thus breaking down the division between native and web applications. A few years ago, some very smart programmers created a C to JavaScript compiler called Emscripten. Around the time of its release, the folks at Unreal decided to see how far they could push this new tool. The result, as you can see on the screen, is the Unreal Engine, running at an acceptable frame rate inside a web browser. So what does this mean? We can take an entire game written in C or C++ and actually get it to run in the browser. Now, while they did compile all their code into JavaScript, they rendered it all inside of a canvas element, allowing them to draw all their widgets and components. However, that violates one of the core tenets of the IUP library, which is, of course, native widgets. We want to bring that idea to the browser. Thus, we present the first cross-platform library using the browser's own native widgets. So normally with Emscripten, you give it your C code and it compiles in JavaScript. Then you have a file ready to run in the browser. It also has current WebAssembly support. But for our case, this isn't quite good enough. In order for us to render native widgets, we need to be able to call into JavaScript to access the DOM APIs. Emscripten didn't necessarily intend for this to be the case. They didn't expect us to be modifying the JavaScript side. However, they do provide us with the ability to write external JavaScript functions, which can then be called from our C code. Thanks to these external function calls, we can now implement the native JavaScript DOM backend. This is what really sets us apart. There are other cross-platform libraries that compile to the web. Qt is one example. However, just like the Unreal team, they draw their own widgets, losing the native experience. For a truly native backend, we have to call into JavaScript. Of course, the end result is a lot of jumping back and forth between C and JavaScript. Constantly jumping around may not sound pleasant, but Eric swears this is still better than Android.
So here's an external example, and you don't have to know much C to deal with this. So here you prototype a function just like you would normally in C, except you preface it with the extern keyword. This tells Emscripten this is going to be an external JavaScript function. Here we write a C function which will make use of this external function. This is returning init, so we're going to start with init. Now let's jump over to JavaScript. This is a library which is going to hold all our external functions. So here's the function. We're basically taking a widget and grabbing the element by that ID, and then this is actually going to return a string, but we're pretending it returns an integer. Back over here, and then you return your init. So pretty simple, actually.
Now, onto the widget creation itself. The user defines the widget they want to create, which we have access to on the C side. The question is, how to get over to JavaScript to render it using the DOM. Emscripten does not allow us to pass objects across the C JavaScript language bridge. We don't get a stack API like in Lua. However, we can pass integers across. Our solution then is to utilize a global ID map that maps integers to objects, thus serving as a proxy. So, how does this work? A call is made into JavaScript, which creates the object as an HTML node, assigns any necessary properties, and then generates a unique ID. This ID is stored in a global container object along with a reference to the object. The ID is then returned back to the C side, which stores it in the widget's data properties. The widget itself isn't passed back and forth, but rather each side references the same ID along with their own interpretation of what the particular widget is. This one-for-one integer ID map allows us to easily access objects on either side, creating a surprising bit of simplicity in a world of constant language shifting.
So here's some really quick examples. This is basic label input text and button. You've got Chrome, Firefox, and Safari. Here's an external dialog, aka pop-up. So you've got Firefox, Safari, and Chrome. Here's a drop-down list, Chrome, Firefox, and Safari. Here's a multiple selection list, Chrome, Firefox, and Safari. And finally, this is a kind of unique IUP one. It's an edit box drop-down. It allows you to either select or kind of start typing and limit your selections. That's Chrome, Firefox, and this is actually Opera, because this is kind of a hack in HTML, and Safari doesn't support it as of yet, or is book.
Because Emscripten follows a C++ paradigm, it assumes we are managing memory manually. There is no garbage collector on the C side. As it follows normal C rules, we use IUP to manage the memory for us. IUP provides map and unmap functions to handle the creation and destruction of widgets. However, the objects we create on the JavaScript side will be garbage collected. How do we prevent that from happening? The answer is the global ID map. Besides solving the problems of object access across the bridge, it also solves our memory management problems. Because an object exists in the ID map, it prevents it from being garbage collected by JavaScript. Otherwise, the object would no longer exist after our remote function was finished and returned to C. Likewise, by calling into JavaScript during IUP's unmap function, we remove the object from the ID map, ensuring it is garbage collected and that both sides always stay in sync. As Eric mentioned earlier, by its design, IUP wants to control the event loop. We cannot let that happen. We need to let the web browser and JavaScript control this, since all the interaction is taking place within the DOM. We have no other option. The native experience IUP promises can be brought to the web. While this more than likely wasn't even a thought during the library's creation, modern tools have made this possible. With the addition of a web backend, your apps become more portable than ever. Forget worrying about operating systems, version differences. If your user's device can run a web browser, it can run your application. You no longer have to make the choice between building a native or a web app. You get both. This returns developer focus to what's important, actually creating your application, and not worrying about system requirements limiting your user base.
So finally, let's bring all the implementations together. A few changes will be needed. The rules are legacy code must continue to work as before, but we are allowed to change and add things as long as we don't break existing stuff. Existing platforms must also be updated to work with the new changes. So we mentioned the event loop 4 times. This is the old way you would start an IUP application. IUP main loop is a blocking function that can be imagined as an infinite while loop that manually pumps the platform's native event loop until the application is finished. That design won't work anymore. So the key idea is, instead of forcing the new platforms to behave like the old, we can make the old behave like the new and make everything cross-platform again. So the old way is on the left and the new way is on the right. First, notice we add 2 callback functions. The IUP entry point callback is required, and that function is now our designated starting point for where the user adds their code. The new int main should be used as you see here and not changed. The second callback is now the designated callback for when the program is quitting. User code gets moved into the IUP entry point function, and IUP close gets moved into the exit callback. So now we'll step through the code on each platform to see why this works. On Cocoa platforms, IUP main loop starts the native event loop. Behind the scenes, we also make sure to call IUP entry point, which is now the place where IUP user code starts. Also note, depending on various factors, IUP main loop may never return. For example, on iOS, apps don't really ever quit. They stay active until the process just gets killed. On Android, there is no int main, since everything starts in Java. Also remember, we must never block the event loop on Android since we do not control it. So internally, we make our Android startup routine in Java call IUP entry point directly. If for some reason you need to change the startup function, you can override the default in the Android manifest.xml, which is an XML file that contains configuration information that every Android app has. With Emscripten, we don't have control over the event loop, and we must never block the event loop. So, IUP main loop must return immediately and cannot block. In our IUP main loop implementation, we call the IUP entry point callback to run the user's code. That runs and returns immediately, and the code flow continues. This means int main runs all the way through to completion and ends. There's a special compile flag for Emscripten that allows the app to stay alive and continue running even though int main has returned. Notice, this is also why we remove IUP close from being called right after IUP main loop. Otherwise, we'd shut down IUP prematurely. So I've updated IUP's existing platforms to work with this new design. When the IUP set function with entry point is called, we now know we want the new behavior. Legacy programs won't have this, so we can maintain backwards compatibility. In IUP main loop, we call the IUP entry point to get things started. Then we run our infinite while loop to pump the event loop. At this point, things are pretty much as before. When the application quits, we end the infinite while loop and call the exit callback, which we'll call IUP close. IUP main loop returns and main finishes. So now our code is cross-platform again. All 4 of our new platforms must operate on the main thread. Apple is unapologetic about it and embraces it. Android we already talked about. And the web doesn't allow threads. IUP doesn't say anything about threads, but we require it now to be only on the main thread. So, we're at the finale. Let's bring everything together. For native development, the big question I'm asked is, how far can I take it? Usually developers have code that is mostly cross-platform, but then needs to reach beyond and do very native and platform-specific things. This usually breaks down into 2 sub-questions. Can I use custom or platform-specific code in my IUP app? So things like the accelerometer, GPS, or random custom libraries. The answer is yes. And here's a silly example, finally with Lua. Last year I showed a Lua Coco demo of a Swedish Chef translator app that uses LPEG. So let's raise the bar for this year. I've ported it to IUP to use across all our platforms. It is one common GUI in IUP, but each platform has a completely different way to access a native speech synthesizer. Windows.
Welke mir to the wonderful world of the Swedish chef. Bork bork bork.
Linux.
Welcome to the wonderful world of the Swedish chef. Bork bork bork.
Mac.
Welcome to the wonderful world of the Mac OS speech synthesizer. Bork bork bork.
iOS.
Welcome to the wonderful world of the iOS EF speech synthesizer. Bork bork bork.
Android.
Welcome to the wonderful world of the Android text-to-speech. Bork bork bork.
And yes, even the web browser.
Welcome to the wonderful world of the web browser. Bork bork bork.
This one is really crazy. We start with all our C code, including IUP, the Lua VM, and LPEG, and compile it into JavaScript using Emscripten. We load all that JavaScript into a web browser. We run a Lua script inside that JS-compiled Lua VM, which is inside the JS web browser VM. And we poke holes out of our C code to call directly into the web APIs in JavaScript for speech and GUI.
The second question is, can I integrate my own custom or native views with IUP? These may be things like map views, video players, PDFs, or even augmented reality views. The answer is also yes. And that's exactly how we wrote IUP in the first place. As an example of this, we'll demonstrate a web widget. Every platform has a different native control to render web content. We'll write the interface so it can work as an IUP program. The web widget is also a convenient widget of last resort, since web widgets have so much functionality baked into them now. So here we are on Windows, Linux, Mac, iOS, Android, and even a web browser inside a web browser. So exciting. So anyway, let's do a quick demo of the web browser. Pardon me when I switch our control here. Alright, cool. Alright, so okay, address loaded up. This is the Blur SDK website. Let's go check out some videos there it's got on here. Check out this Raspberry Pi. So there you are. A YouTube video from a website playing in a web browser within a web browser. Alright, so what would you use this for? Maybe you want to embed YouTube videos into your app. Show a PDF if you don't have a native PDF viewer. Mac views in platforms that don't have native versions. For example, there's a cable company that already created a web app showing the channels in the TV schedule. They commissioned a separate native app, but they didn't want to re-implement this entire thing they already did. So they used a web view to show the schedule and channel listing within their native app. So the size is small too. This is a screenshot of Linux. Unlike, say, Electron, we don't need to embed a whole Chrome instance. This is already provided by the OS. As you can see, the entire app is under 1 megabyte of native binaries.
All the source repositories can be found on GitHub.